Hi everyone, this is Miss Flores coming to you from home. I'm sorry I couldn't be there with you today, but I'm not feeling well. So I've recorded this lesson for you. So today we're going to be going over graphing rational functions, which is actually really similar to what we did yesterday when we were graphing the reciprocal functions. But there's a little bit more complexity to it. So for graphing rational functions, what we first need to understand is what a rational function is. So a rational function is when we have a function that is equal to another function. Let's go with over a third function. So we basically have an expression over another expression. Okay, that's what a rational function is. Because we have a function in the denominator, okay, we end up with some very interesting graphs. Because we have this function in the denominator, this actually changes a lot of things. And because it's set as a fraction, this numerator also changes the way that this function works. So your rational function is not going to look like either of your functions in the numerator or denominator. Is going to be something completely different. Okay, so when we are working with graphing rational functions, okay, there's some things that we need to look for. So I'm going to show you in an example what we're looking for. So hopefully Mrs. Loda was able to get you guys the handout that's asymptotes, holes, and graphing rational functions. I also put this link on Google Classroom, so she wasn't able to print that out for you. You can also look this up on Google Classroom. There is an example in that handout where they show us that we have the function of x cubed plus x squared over x cubed minus 4x squared plus 4x. So as you can see, we have a function in the numerator and we have a different function in the denominator. Okay, but these two functions make up the actual function that we're interested in, right? The f of x. So what we do with these functions, the first thing that we want to look for is holes. Okay, so that's the first thing you want to do is you're looking for holes in the function. And the way that we find holes in the function is we take our function and we factor out the two expressions, the numerator and the denominator. Okay, and we do that separately. So if I take this function and I factor it out, I can already see that the thing that they have, what I'm looking for is factors in common. Okay, so if the numerator and the denominator have factors in common, then it creates holes in the graph, okay, where whatever number we get from that hole, it doesn't exist in the function. Okay, so we have to physically draw a hole in the line, indicating that that number or that coordinate doesn't exist in our function. Okay, so when I factor this out, I can factor an x out of the top. I know that I can factor out x squared out of the top, but I can't factor out x squared from the bottom, from the denominator, so I'm only going to factor out 1x because that's what they have in common. So I can factor out an x, and I'm left with x squared plus x over, and I'm factoring out an x from the denominator, and I end up with, inside the parentheses, x squared minus 4x plus 4. Okay, so what they have in common is x. Okay, so f of x, when it is equal to x, is, well, actually no, hold on, let me go back. Not f of x. When f of x is 0, whatever x is equal to, that's where my hole is. So my f of x is equal to x, I'm going to change that to a 0. So when f of x is 0, x is equal to 0. So that means that the point 0, 0 is the hole in my function. So at that point, the function does not exist. Okay, so you're going to physically draw a hole in the line. And that's how you find your holes. You could have more than one hole. If you had a function, for example, let's call this g of x. If you had a function where you were able to factor out, let's say, x minus 2 from both the top and the bottom, and let's say that this was x plus 3, and then on the bottom you also had x minus 2 factored out, and we'll make this something else. That, okay, we're not going to work with that anyway. But see how they both have x minus 2? That means that at x minus 2 is equal to 0, there's a hole. So where x is equal to 0, which means that at the point 2, 0, 2 comma 0, there's a hole. Or actually any time that there's not 2 comma 0, I'm sorry. Let me go back to that. That's how you find it. That's not where the hole is. In your graph, okay, so it doesn't want to work. There it goes. In your graph, anytime that x is equal to 2, there's going to be a hole. So like when you graph your function at x is equal to 2, wherever your function is at 2, like here, there will be a hole in that function. Okay. All right. The next thing that you need to find, let me change colors. All right. So the next thing that you need to find are your asymptotes. Okay. And for your asymptotes, there's two different ones. So we have our vertical asymptotes, which I will abbreviate, and then we have our horizontal asymptotes. So the vertical asymptotes, let me talk about those first. For the vertical asymptotes, you're going to set your denominator equal to 0. So in our original example, our denominator here, we're going to set that equal to 0. So we have x cubed plus, minus 4x squared plus 4x is equal to 0. So wherever that is equal to 0, that's what we're going to set. So to solve this, I'm going to factor out my x.